Good afternoon, everyone. I am Dr. Padmaja Gugila, currently serving as the Associate Dean of College of Engineering, Technology, and Physical Sciences, and also serving as the Interim Chair of Physics, Chemistry, and Mathematics. I welcome you all to the inaugural Physics Colloquium series of PARS, and I am sure most of you are already aware of this partnership. This is a partnership for radiation studies, and we abbreviate it as PARS, P-A-R-S, and we received the funding for $2.83 million from our National Nuclear Security Administration, and which is new grant for Alabama A&M University, and we are very much excited that as a part of this grant, we would like to bring all the experts from national laboratories to come to A&M, either Zoom or in person. We want to make sure that we get all their expertise to the campus, and we want to make sure that all our students are aware of what's going on currently at the national laboratories, and we would like our students to gain more insight as well as more excited about the research happening at the laboratory. And I'm very excited to announce our first speaker for this series. That is Dr. Manish Sharma, and he's a staff scientist from Pacific Northwest National Laboratory, which is PNNL, and it is located at Richland, Washington. And he's going to give a very interesting topic, and that is about the one which is World War II, gamma spectroscopy of uranium cube from World War II. And Dr. Sharma has a huge, experience in terms of, working with these crystals. And he is a physicist at National Security Directorate at Pacific Northwest National Laboratory. He obtained his PhD in nuclear engineering from Missouri University of Science and Technology in the year 2016. Before joining PNNL, Dr. Sharma was working as an assistant professor in the Department of Nuclear Engineering at Khalifa University, United Arab Emirates. In the years of 2016 to 2018, he also held a postdoctoral position in the Department of Nuclear Engineering and Radiological Science at University of Michigan, Ann Arbor. And Dr. Sharma is an expert in developing advanced system, software, and algorithms for nuclear explosion monitoring and security tasks. At University of Michigan, Dr. Sharma developed and characterized several composite scintillation detectors and led and designed development of University of Michigan Neutron Science Laboratory. And I welcome Dr. Sharma, and floor is yours. And we give you a bulldog welcome. And since we are virtual, but I would like to make sure that all our students are here and welcoming you.
All right, thanks, Patty. So before I kick off, you can hear me fine?
Yes, yes.
I'll stop my video as well, and you can see my screen as well.
You don't have to stop your video, of course, but anyways, yes, we can see your screen, yes.
Okay. Cool. So thanks for the warm introduction. It's just an honor to basically kick off this seminar series for PARS. I'm the victim. I'm the first one who is kicking this off, but I'm 100% sure you guys will enjoy this presentation. And again, I'm honored to be here. Basically, I'm just going to talk about some of the finest facilities that we have at PNNL, specifically motivating students to come to STEM. That's the whole point of having PARS, and not just STEM, just national security, nuclear engineering. And I hope to convey that message through the study that we have done. So we're going to talk about uranium cube, as Patty has already mentioned. This dated back to World War II, so I will go into the details. And on the right, the picture that you see is one of the finest multi-million-dollar facility that we are responsible for in the installation and operation of this beast. Okay, so moving forward, here is the overview of the presentation. basically, we will start with the uranium cube. Like, what is that cube are we talking about? How does that relate to World War II? Of course, I'm not an history expert, but I know enough history to connect it to the uranium cube. Why did we even study the uranium cube? There are many other things to do in life. So I will try to ramp up the motivation there, together with the shallow underground laboratory that we have here, which is an underground laboratory, one of the finest PNNL facilities, which has multi-million dollar equipment, as you can see on the right. So I will talk about in details about these detection systems. And if you're lucky, you can always come here as an intern for PARS or some other program to work on these finest system with the amazing team that I have at PNNL. So finally, with the conclusions for this talk. So let's go back to the time where everybody was racing towards nuclear, and that was a time in World War II. Specifically, I'm just going to talk about two perspectives, one from the German side, one from the Germany side, and one from the American side, or the Germany and the America. Both were racing for nuclear, both on the peaceful side of nuclear engineering, or the atomic bomb, or the uh, the non-nuclear side, the non-peaceful side for the nuclear engineering. So let's talk about the Germany perspective first. So we had two groups there who were racing towards achieving criticality, nuclear criticality, and these groups were led by two major scientists. The first one was Heisenberg, the same Heisenberg that you may have heard about the uncertainty principle and all the amazing equations and approaches that we still follow today. So Heisenberg was leading one group to race for the criticality, and the other group was from Kurt. This person from Germany was also leading to achieve criticality, and they were using different kinds of uranium because they had like no access to the Monte Carlo codes at that moment, right? 1940s, we are talking about. Today we have MCN, PGN4, and all other fancy stuff to do the modeling, to do the criticality. You can do that in MCNP to do the measurements or to get an estimate of the criticality. So they were playing with the different geometries, as you can see on the right. Heisenberg's group was playing with the plates, which is the top picture. Let me just turn on my laser pointer here. So Heisenberg's group was using these plates on the right, and Kurt was using the cubes, as you can see here, for uranium in the reactor that I'm going to talk about in a minute. And they were just doing the best they can. I mean, they were playing with different geometries, both the powder and the solid form, and the moderators as well. They were playing with the dry ice, the paraffin, the graphite, the heavy water, you name it. At that moment, they did like 20 experiments just again to achieve criticality in the reactor. So how did their reactor look like? And you can imagine it's again 1940s. I mean, they have to be strategic. For instance, if you see the picture on the right, which basically shows the location, the physical location of the reactor, the red box basically shows the entrance to the nuclear reactor. And it was strategic enough because this was beneath the church. The reason was because Germans were thinking that any American is less likely to guess that a reactor will be below church and hit a church than any other place. So this was strategically located below or beneath the church. If you look at the same picture today, which is like the right bottom picture, there is a museum right now there, which basically has a prototype of the reactor that was demolished later, as I'll talk about. But right now there is a museum which basically has a prototype of the B8 reactor, one of the experiments that these two groups were doing. So you can see those cubes basically hanging in the form of a chandelier. You can imagine, and then the graphite moderator. For any change in the flux, they were pulling the chandelier, the uranium cube, down and up to alter the flux. Picture on the left basically shows the irradiation that they were doing at that particular time. They had like a Rabi neutron source, as you can see here, to achieve fission. The good thing was the reactor could not go critical for the reasons I'll talk about. in details. So since we have talked about the side of Germans, let's talk about Americans. United States military at that particular time was sort of aware that something is cooking there in Germany. So we came up with a plan. The military came up with a plan called Elsos mission, which you can see here. And this mission was led by two awesome guys, Lieutenant Boris Pash and Samuel Godsmith. As you can see the pictures here, they are leading this whole mission. And this is again April 1945 that we are talking about. The main aim was to unravel what German scientists are trying to achieve, especially in the nuclear research efforts. On the right, there is one picture that you can see here for the Heisenberg. So Heisenberg was doing experiment around the time when American basically planned to attack and demolish the reactor. Knowing this beforehand, he basically ran. This is a funny story and fun fact. He basically ran with like a few cubes in his backpack. So you can imagine each cube was like 2.5 kilograms. So that essentially means like 20 pounds of uranium cube in his backpack. He was just biking straight for like 3 days with a few cubes in his backpack. How do we know this fact? Well, 20 years after the fact, there were some cubes that were recovered from the cottage near to the cottage of Heisenberg. Basically, he tried to throw the uranium cubes into the river, and some kids basically found the uranium cube like 20 years after the fact. So yeah, that's a fun fact about the story. So where are these cubes? And you can see these are the cubes that were recovered by demolishing the reactor that I showed in the last slide. And here are the men at work, as you can see, demolishing the whole B8 reactor. So where are the cubes sitting right now? There were like 700 to 800 cubes that were there. We do not know the exact location of those cubes because some of those cubes were offered like a souvenir to diplomats. So we don't even know the exact location of each and every cube, but some of the location are given here. For instance, in Germany, some of the museums, the federal office, for instance, has one of few of those cubes. In the United States, PNNL holds one because we are awesome. Washington State Museum, museum in Washington, D.C. holds one. The Harvard University and the Rochester Institute has one. There is a very nice article by Physics Today, which basically enlists the possible locations or the known locations for these cubes. So here was the objective for this study. We just wanted to know more about this cube. Of course, the simplest thing you can ever do is just break something apart and try to determine the composition using the chemical techniques. But unfortunately, that's not the case here. This is one of the finest samples that you're talking about. It's expensive. It's a souvenir. You cannot just break everything that you see. So we were not allowed to break it on our end. And this was the main crux of this study, to do the gamma spectroscopy, the first gamma spectroscopy of this uranium cube that you see on the right. And it's a non-destructive way, so even better to determine the isotopic composition, for example, the uranium isotopes that you see on the left, to answer whether it was a natural or the enriched uranium that Germans were trying to irradiate. And of course, date this back to World War II. If we are doing the right mathematics, if we are using the right facilities, the multi-million-dollar facilities, of course, we cannot doubt those. But if we are doing everything right, it should date back to the time of World War II. So this is all what we achieved using the gamma spectroscopy of this cube. So this cube was about 5 by 5 by 5 centimeter in dimensions. If you do the math with the density of the uranium, you will get like a mass of 2.5 kilograms. So each of this cube is heavy. I mean, so now let's talk about the finest facilities that I was trying to cover earlier. So Shallow Underground Laboratory at PNNL was commissioned in 2010. This is the underground laboratory, 40 feet down. You basically can see the car here on the right, which is basically like the first floor. And then you take the elevator to just basically go down and do some fun experiments. So we have many different labs there, including the measurement laboratory that I'm going to talk about. And we are one of the finest producers of the purest copper ever possible. So we do amazing stuff underground there. We have clean detector fabrication and machining there as well. And by going underground, what do we do? Well, if you go underground, you reduce the background. So for instance, if you just go out, you just have one detector, let's say the radiation detector, you just go out above ground and do some measurement, you will see that there exists background, the cosmic background, which basically pop up the counts in your detector, which basically interferes with the measurement of samples. So one thing that you do by going underground is you basically reduce the background that comes from the cosmic radiation. So by doing that, you basically achieve sensitivity such that you have less, 100 times less neutrons and 6 times less muons just by going about 40 feet deep underground. So once you have reduced background, of course, you achieve more sensitivity. So that was the whole point of spending money for the development of this laboratory. So in routine operations, the shallow underground laboratory, again, is the finest facility. This is used especially for the campaigns of interest of NNSA and DITRA. And also we have ties with other universities and other international collaborations as well. For instance, UK, France. So we collaborate heavily on that aspect. So let's talk about the system. So the systems that are installed in the underground laboratory, 2 of these systems, of course, there is one more system that we developed over time. I'm not going to talk about that because the cube was not studied on that system, but that could be a part of the next seminar series. So 2 detectors that were used in uranium cube studies was the SAGE detector, the small anode germanium detector. This is a single detector system, as you can see, as I'm highlighting here. And the other one is a beast, the Argo, which is like 20 detector system. It's much more fancier, much more sensitive than SAGE. So we measure the uranium in both of these detectors. And these detectors were purchased from Miriam Technologies, in case if you are ever interested in knowing more about these detectors or purchasing those in the near future. So let's talk about SAGE first. I'm not going to go into too much of details, but this is one of the most sensitive detectors from Miriam Technologies. It basically has a well kind of structure, as you can see in the bottom here. Once you have a well kind of structure, you basically put your sample down into this well. Once you do that, you cover your sample almost like in 4 pi direction. Once you do that, you achieve a higher detection efficiency because you are basically capturing each and every gamma that is coming out of your sample from any direction. So that's how you achieve really good sensitivity with the SAGE detector. This also has like a small anode design, which basically reduces the capacitance and the noise. So once you reduce the noise interference, you basically achieve even more sensitivity. So this SAGE detector, the one in the bottom right, is a schematic for the SAGE detector. You can see the detector in the middle. And then this is surrounded with the shield, the ultra low background shield. By again having a shield around the detector, you reduce the background because it's interfering with your sample measurement. So how do you reject the background? Well, if you imagine a cosmic event or a cosmic background event appearing and interacting with the detector, we have another detector at the top, the cosmic veto detector. For this interaction in the veto and the SAGE detector, using the time of appearance of 2 events, you basically can reject this particular event, saying that this is the background event, and all you measure is the sample gammas or the gamma that comes off from your sample. These detectors are, of course, hooked up to the PC, the computer, as you can see on the bottom in the bottom picture. And in the top, you can see the SAGE detector. In real, this is the bottom of the detector going up, and this is the shield, which was this shield that I was talking about. And of course, the cosmic veto system is sitting at the top. If you want to place the sample, you basically open this this shield, which is like these 2 handles that you see, and you put the sample right in the middle of the well. So now let's talk about the other fancy system, which is much fancier than the SAGE detector system, which is the Argo, or a multi detector system, which has like 20 detectors in it when it is fully operated. You can see this has a much heavier footprint and is much more expensive than the SAGE detection system. So if you look at this picture on the right, these are the two detectors, like the HPG detectors that we have in the up and down configuration, and is surrounded with 12 sodium iodide detectors when it's operating in full configuration. In the picture in the bottom, you can see this 12 sodium iodide detectors basically covering each and every possible direction for giving directional functionality and reduction of the background continuum or the Compton continuum. So you have 12 detectors of sodium iodide and 2 HPG detectors. So that gives you 14. And then you have 6 additional detectors, which is like the cosmic veto panel. The black panels that you see here, they are covering the sides of this whole assembly. Basically, these are the cosmic veto system to reduce the background, like the technique that I just showed in the last slide. You can see the veto panels here as well. So whenever you want to place the sample, you basically use this area, and then of course you put your hands into these funny things, and then you finally place your sample right on top of the bottom of the detector if it is not too heavy. So having these many detectors, and these are optimized as well, having these many detectors optimized for low energy gamma spec as well, you achieve coincidence functionality because you are able to capture as much as radiation as possible. In singles and both in coincidence, and together with positron detection or Compton suppression using the sodium iodide, and of course the directional detection with this multi-million-dollar facility. So talking about the measurement, the uranium cube that was measured on the SAGE detector, you can see the whole model is here. You have the uranium cube sitting right on the top of the SAGE detector, and you have the urethane, polyurethane foam in between. As you can see, if you look at the uranium cube picture, you see this yellow area, which is basically your foam. So we try to model the foam as well for accurate quantification for the radionuclides. The uranium cube was just measured for 10 minutes for this particular case, and you can see in the bottom is a gamma spec, is a gamma spectra for the uranium cube, and you can clearly see the daughters of the uranium, like protactinium-234, for instance, and of course our friend, the uranium-235. These peaks that you see are from uranium-235 present in the uranium cube samples. So once we have identified with the energies that these are our lines, these are our uranium lines, the next step was to do the quantification, like how much of uranium is it present in the sample. So that's what we did in the left picture. Basically, the blue line, the dashed line, shows you if it is natural uranium, your data point should lie somewhere around that, area. So you can see all the measurements that we did. These are the red data points, basically matched to the natural uranium concentration that we would expect in this uranium cube. And you can see, for instance, this is like 140 keV, a data point. If you go back here, this is the uranium line around 140 keV as that data point. So the results agreed between different lines, which is a good thing. And again, confirming that it's a natural uranium sample. One of the things that was not achieved here was the presence of 234, the uranium-234. So we were able to again identify 235 and 238, looking at these daughters and uranium-235 with the SAGE measurement. So that was a motivation for the Argo study that we did to basically measure the uranium-234, because the gammas that comes off from uranium-234 are in low energy and less intense as well. So here is the picture for the Argo system when we measured the uranium cube in between the two up-looking and down-looking detector, as you can see here. And on the right top is basically the energy spec from the Argo detector. And here clearly you can see the uranium-234, like 120 keV. This little bump that you see is from uranium 234, and the intensity is pretty low. But since Argo is much more sensitive, and together with the measurement was done for 6 days as opposed to 10 minutes on SAGE detector, we were able to see the uranium-234 concentration or energy lines there. If we do the math, and again, I'm not going to talk about the math, but using the decay equations, the basic equations that you study in nuclear engineering, you can determine the isotopic ratios for these energy lines for uranium-234, just like the way we did for the uranium-235 in the last slide. And you can see they pretty much agree with each other, and together with the work from other researcher with another uranium cube. Yeah. And the picture in the bottom is basically showing the same picture that I showed in the last slide, and not for the SAGE. Right now, it's for the Argo, for the two detectors. You can see, again, the data points basically agree and say that this was the natural uranium, not the enriched uranium, which was the reason the Germans were not able to achieve the criticality, because the things would have been different if the concentration for uranium-235 would have been enriched beyond the natural uranium concentration. So the second objective of this study was dating it back to World War. If we are doing the right things, which we are, we should be able to get a meaningful results. That was the whole point of this study. So how do you date a material using gamma spectroscopy? Well, what you do is you measure the parent and you measure the daughter, and based on the activity ratio or based on the concentration ratio of these two entities, you can determine the age that cube or the material was cast. So you basically come up with this curve called the Bateman equation. If you study that in your nuclear engineering curriculum, basically you use those equations to determine the age with respect to the activity of the daughter. So here we studied the bismuth-214, which is one of the daughter products for uranium-234, as you can imagine, the different concentrations. And using that, we were able to quantify the age. As you can see, using the different lines for bismuth-214, you can determine the age of that cube. And on average, we came about like 76 years in the past. This uranium cube was cast, which was around 1944. And you can imagine this study was done in 2020. So if you do the math, it was around 1940. This cube was cast with an uncertainty of about 7 years, like about 10% of uncertainty in the activity is generally what we get here. So this matched, the conclusion basically matched to what we were expecting, because the cubes, as you can see on the left, were captured by the American military in around 1945. So that gives us the confidence that our systems did well in measuring the low energy, low sensitive measurements with the uranium cube. So here are the prominent conclusions about this presentation. First, we spoke about the shallow underground facility, one of the finest facility at PNNL. And again, we welcome you as an intern, as a graduate student, to work with us as well on such facilities. Our group is crazy in doing measurements of various samples, biological, extraterrestrial, like meteorites, or environmental samples, or a sample like this. I mean, so if you want to join our team, you are always welcome. We are catering the NNSA and DITRA and their campaigns. And this study basically talked about the uranium cube that we studied using the single and the multi-detector systems installed in the shallow underground laboratory at PNNL. And this was the first measurement of isotopic ratios for the uranium cubes, which are also called Heisenberg cube, which makes sense because Heisenberg was the leading scientist on that front. So this was the first gamma spectroscopy ever performed. And the results agreed, indicating that this is natural uranium dating back to 1940s, which makes sense. This study was supported by NNSA, so we acknowledge the support from the DOE and NNSA for this work. Here are some of the references. I'll just talk about the top one, which basically talks about the results that I have just presented. If you are interested even more, you can go for this publication. And if you're interested in more on the history side for the uranium cube, these are the one in the middle are the references which basically talk about the location of the uranium cube and more history on the Germany and the American side. So here is a conclusion for my presentation, and I'm open to any questions you may have.
Thank you so much, Dr. Sharma. That was very interesting. So if you have any questions, please feel free to ask Dr. Sharma now.
Dr. Sharma, can you hear us?
Yes.
Okay, so this is Stephen Babalola. Thank you so much. This means a lot to us. You taking time to talk to us, especially talk to the students about your work and the facilities that are available for us to utilize at PNNL. Guys, this is an opportunity for us to ask Dr. Sharma any question about the work or about the facility or about just anything that interests you from what you press open.
So, what does your kind of day consist of working at a national level? What do you do on a day-to-day basis?
Sorry, I'm having difficulty on my end. Can you
Yeah,
please repeat that?
Have to repeat his question. His question is, and correct me if I'm wrong, what does a day look like working at a national lab?
Oh, it's an amazing opportunity. I enjoy every bits and pieces, especially not just at PNNL with my team. You can imagine with this kind of study, these are the possibilities that these are the opportunities that you do not get everywhere. So I have worked at many places, and again, I'm not just bragging about the place I am, not just bragging about PNNL, but in general, it's more like we do a lot of research on samples like the one I have presented. So the conclusions are pretty strong. So it's just fun to just know about more on the history side, more on the research side. And the fact that I still use the equations and the mathematical approaches that I learned during my undergraduate schooling and then graduate schooling, I still use those on day-to-day basis. So for me, it's more fun on this aspect. Yeah, so I spend more time in the research. You also have some commitments to do the operation side of catering again to DITRA and NNSA for experimental measurements. So some folks in my team, including myself, we are involved in measurement of the samples for DOE as well. So it's more on the research side, and then again you get the opportunity to measure very unique samples that you may not be able to get anywhere else.
Thank you.
Yep.
So since Cornelius asked the question, so let me ask this question on behalf of our students too. So what experience you had before you entered PNNL and this training, like, working on all these instruments, were you all aware of that before you entered the job, this particular job, or you had some training, you had to go through some training, or what? How did you really manage to work with all this sophisticated instrumentation?
So it's a mix of that, Patty. And again, I'm talking as a postdoc. So when I joined here, I already had my PhD. I already had some experience in Michigan. So generally speaking, I had some background, both in gamma spectroscopy and not just gammas, but working with neutrons as well. At that point, yes, I had some experiences with the radiation measurement, but here the systems were much more sensitive and much more fancier than the ones that I have worked. So I was well aware of the physics, and I was trained on the other aspects to explore my skills as well. So it was a mix of like knowing half of the things and then exploring the other half.
Oh, okay.
And especially with the students, we generally try to understand when they come as interns or as a graduate student. We understand that you cannot really know everything in the world. I mean, you always have time to learn things, but the passion is really important. And then this is where we as scientists try to bring you on board and try to train you for the codes, for the systems, and help you out maintain that kind of culture that if you have any issues, you can always knock our doors, and then we will try to help out with the measurements and the troubles that you may be having in your projects.
Okay, Dr. Sharma, were you able to determine the amount of exposure that the people had at that church, or any of the people who were carrying around these cubes?
So you mean exposure to the personnel that were working there?
Yes.
No, I mean, that was not the part of this study. They were using the rabies source. I don't recall even the activity of the source, but it's documented somewhere. But we did not measure that aspect in this particular study.
Okay.
Thanks for the question, though.
Hey, Manish, I have a follow-up question to
Yes.
that, and the question is, for around the World War II, the major challenge in developing the bomb was to be able to enrich the uranium. So my question is, the cubes, the casted cube that you guys have, did you see any sign of some type of enrichment, or do they look like the naturally occurring ores of uranium?
So in the study that we did, and this is sort of a hobby project as well, but we did not measure any enrichment in the uranium, which is also expected, like you are saying, and the techniques that existed at that particular time were not advanced enough to do the enrichment. So on the gamma spec side that I did, all the data basically matched to natural uranium, and it was not just the 235, even the 234 ratio that I showed in the slides as well. They all matched to natural uranium. Things would have been different. It was enriched uranium, but this is sort of an ongoing hobby kind of project that we are always waiting to work on this as well, to look for another possible signatures of irradiation, because we know that the cubes were exposed to neutrons. So were there any fission products that were produced at that particular time that we can still measure? We still want to do that, but yeah, that's like the future work that we have.
Thank you.
Yep.
So
John has the hand up. What's up, John?
I just had a quick question. Great talk. Firstly, Manish as well. What advice would you give the students in terms of, getting out there and helping establish their careers and doing the things they want to do? Is there any lessons you can kind of share with them, or pointers and opportunities you might recommend they seek and so on?
Thanks, John. Thanks for appreciating my effort as well for the talk. So again, I come from a different background, in a sense that I come from a different country. I had a different education and things like that. But I have developed a philosophy over the years as well. Like my friends used to say during my undergraduate days that the equations or the mathematics that we are using 99% of the time, they won't be useful. Which is not true in my case. I proved them wrong, that whatever equations or mathematics that I learned during my undergraduate school, and I excelled having good GPAs. That was the first thing that I always did. That how would you prove that you are awesome, right? I mean, you need to quantify your awesomeness somehow. So I agree that GPA is not the only thing, but I would highly encourage you to pursue a good GPA first in your undergraduate days, and always be passionate about science, doing something for your country. I mean, you have the opportunity to come to, let's say, PNNL, for instance, and demonstrate your passion to science. So be passionate about science, keep pushing it, have good GPAs, and yeah, that is a major advice I can give overall, just to demonstrate excellence in whatever you do.
I have a question. So my question is, whenever you guys do all of like the measurements and the analysis, what kind of do you guys use any like programs to like plot everything down? And like, what kind of like coding programs you guys use?
So as I understand the question is, what kinds of program do we use for analysis?
Yes.
So that depends on your interest, actually. I mean, that also differs group by group, but if you just talk about myself only and my team in general, we use a lot of Python in analyzing the data that comes off from the system that you guys have just seen. So Python is more on the data analysis side or interpreting the data. And the other code that we use a lot, and I was talking to Jonathan Lasseter about that, is a GN4 or another Monte Carlo code, MCNP. We don't use it a lot, but I mean, that could be helpful sometimes. But we use GN4 here at PNNL as well for the Monte Carlo coding, right? Every time you cannot just do the experiment. Sometimes simulations are helpful in understanding the response of your detector or characterizing your detectors in advance of doing an experiment. So generally we use Python. Some of the MATLAB features I used in some of the projects, but it's generally Python or basic software like Microsoft Excel on day-to-day routine operations that I use. And of course, this is except the commercial software that we use for data collection, which is from Meridian Technologies, but that is completely different.
Thank you.
Yep.
Hey, Manish, in addition to, or rather, follow up to the last question.
Yeah.
When you first showed your video, the students saw your background and they were like, wow, you do have a lot of cool stuff. That's what they said. Do you want to tell us about some of those cool stuff we see behind you?
So I should mention that this is the cool stuff I have in the back. I completely agree. There is nothing radioactive in the back, just to be sure. And I am above ground as well, so I'm not underground. And I should also mention that this is the baby for one of my team members, Ryan O'Mara. I mean, we are developing a supercomputer here, and this is all under Jonathan Burnett. As a team, we are developing a supercomputer here, as you can see in the back, and maybe Ryan in the future or another team member from our team can basically talk about this supercomputer. This is a low-cost Raspberry Pi supercomputer. Again, I'm not the expert on this, but yeah, I mean, this is a supercomputer we are trying to build. It's going to have like 1,000 cores, and it should be able to do computations really faster than the normal PCs and even the other supercomputers all around the world. I'm not sure if John or Ryan would like to chime in and give a broad overview on this, but that's their baby.
I don't mind. I could quickly say something. So I'm John Burnett. I work with Manish. I have the pleasure of working with him the last, how long, Manish? 3 or 4 years?
Three.
Yes. So the work we do, we need access to quite powerful computers. So we have a supercomputer here, and it's called Deception. Manish has done some fantastic work on it. But we use it quite routinely, and we decided we can actually do a lot of that work by building our own low-cost, small-scale supercomputer. And we like playing with our toys and kind of making things and trying to do kind of things that are useful for others as well. So we're familiar with the Raspberry Pi system, these little small computers that start at $35. And the idea was, could we join enough of them together to make a supercomputer? So instead of it costing millions of dollars, it costs 10, 20, 30, 40K, depending on how many cores you have. And we've set the record now in the US for the maximum number of cores with the Raspberry Pi 4. That's about half of them on the wall behind Manish. The other half are actually on the other side of that wall in my office where I'm speaking right now. We have 800 cores. We'll go a lot more. It's pretty fast. And, this is technology that it's useful for our work, but a real driver, to be honest, is to produce something other folks can use. A multi-million-dollar investment on supercomputers beyond the reach of most institutions and other countries as well. But 10, 20, 30, 40K, it's not. And okay, it may not be as fast as the latest and greatest supercomputer, but it's pretty good. it allows some very powerful research to be done. So that's one of the cool things, and just to kind of add to Manish's great advice on kind of the career things, my philosophy is very similar to Manish. Work hard, concentrate on your studies, seek the opportunities out there, and kind of make friends with people as well. Make those contacts. It's a small world we live in, and make friendships and build relationships. And I think if you do stuff like that and you work really hard and seek the opportunities out there, you can do kind of cool things and do things you're interested in as well. Ultimately, as long as they're not kind of super crazy, you've got to earn a living. Do things you're interested in that you can enjoy in your career. Because if you do that, you're going to be fulfilled and you're also going to do well as well. I went a bit off subject there, but I hope that answers the question.
Thank you.
I know that you said this is something that you're passionate about. I was just wondering if you had an opportunity to go back to where it all began when Heisenberg decided to work in a church and do the museum or anything.
Dr. Manish, did you hear the question?
No, I was just trying to clear the background in my head. It's interfering with the noise in the background. So can you please repeat it again?
Okay, so I'm gonna try to repeat it correctly in the background. So the question is, since you are so passionate about the work, especially with the uranium cubes, did you ever get a chance to go back or to go to the site where it all began, the site where those cubes were recovered?
I wish if the project can support that, but I would like to. I mean, I have not visited Germany, so that could be on my bucket list, but I never had the chance to go there. But I have heard that they have a museum and then they have the prototype reactor there. But that's a great question. I keep noting in my head the things that I should be doing before retiring. So that could be on my bucket list. If the project can support it, that's even better. But I did not until today, yeah. Did I answer the right question?
Hello, Dr. Sharma. I have a question.
Yes.
This is about the gamma spectroscopy quantification page. When you say quantification, do you mean against the uranium-238?
Right. So quantification, again, so there are two keywords here. One is identification, I mean, at least for me, and the other one is quantification. Identification is you see the uranium lines at particular energy. That's your identification. That's telling you uranium-235 is there. Now, the next question is, if it is there, how much is it? So that's your quantification. How you do it? Well, you measure it with respect to uranium concentration. For instance, when you measure uranium-235 with respect to 238 or uranium-234 with respect to 238, you can measure and again quantify that in that relative term to determine whether it's a natural uranium or the enriched uranium. So these numbers that you get as a ratios, you can determine that. So when I said quantification, I meant with respect to uranium-238.
Thank you very much.
Yep, thank you.
Any other questions? So in the absence of, oh yeah, please go ahead.
Hello, I would like to ask you a question.
Yeah.
Can I?
Please.
Okay. The excited uranium nucleus usually undergoes alpha, beta, gamma decays. What the probability for each one? That's my first question. Second question is, for the 5 times 5 times 5 centimeter the cube, the radiation, the flux, the gamma ray, the flux, what the flux, like per second, how many photon, how many gamma rays emitted by such a kind of a cube, and how compared to the safe level, maybe much higher than the safe level, right? Okay.
So I did some maths a long time ago. I don't remember that number, but at least for uranium-234, I was doing some math for the neutrons per second that are coming out. I honestly don't know. John, do you recall by any chance, were there any, I remember there were some security protocols we had to follow, but I don't recall if the radiation exposure was high, really high.
The dose is trivial because the fissile component, the 235 uranium's very small in natural uranium. The natural uranium is also self-shielding as well. It's quite heavy and dense. So there's very, very little dose in terms of it's quite, it's reasonably safe to handle. There was security precautions though. It actually was regarded as safeguarded material because it, had been from an intended reactor. So it had to be very carefully kind of monitored and locked away, and we had to handle it very securely. But there wasn't really any safety precautions other than what we normally do, what we normally follow for, radioactive materials. We wear clean room outfits. We're dressed up and it's gloved, it's bagged up. We follow those precautions, but there wasn't a significant dose hazard.
Okay, thank you. By the way, do you in your group do you also do research about the theoretical mechanism for the radionuclide to decay? Because recently in our group we also conducting some research about the particle or nucleus decay, like a diproton decay from a proton-rich heavy nuclei, and also particle decay in quark level, not at particle level. Usually we consider the uranium like excited and jump to the ground state and they emit a photon. That looks like based on the electromagnetic interaction. For the beta decay, that should be weak interaction, and for the alpha decay by the uranium should be the strong interaction. So do you do some theoretical research in this hand?
So if you talk about in general in PNNL, yes, we do. I was a part of another group here at PNNL where we were doing the beta gamma spectroscopy. So there we were measuring the charged particles that you're talking about. And in principle, yes, I mean, we have some projects that basically are targeted to measure the electrons, although not protons, but the electrons, the betas or the internal conversion electrons, and not just that, the coincidence spectroscopy as well. So for instance, just like gamma gamma coincidence, you similarly have beta gamma coincidence. So you can use like silicon detectors to basically do that. So there are groups here at PNNL which are heavily doing research on that front.
Okay, thank you.
Thank you.
Thanks.
Do we have any more questions from anyone? If we don't have any questions, let's thank Dr. Sharma for his time and expertise, sharing all his experiences. Thank you so much.
Thank you.
Thank you so much, Dr. Sharma. So we'll meet again now with the next interesting talk. Thank you again.
Thanks, Patty. Thank you. Thank you, Stephen. Thank you. Take care.
Thank you.
Bye, everyone. See you next time.